one of the 5G scenario that introduced in release 16 and release 17, and then integrated sensing and communication. This is a very active research in 6G networks. Okay, so the story is I'll tell you about in-band full duplex radio, and then you can see this in-band full duplex radio is ideally suited to these two scenarios. One is integrated access and backhaul, and other one is integrated sensing and communication. Okay. So, so this is the kind of a overview of my talk. I'll start give you some motivation and challenges for belong 5G and 6G network. Then I'll talk about what is in-band full duplex communication. To realize in-band full duplex communication, we need to cancel self-interference, which is the very challenging task. So we will spend more time on what is this self-interference is and how to cancel this one, etc. Then, as I said, in-band full duplex radio is ideally suited for these two applications, which is integrated access and backhaul. This is the 3GPP scenario in release 16 and 17 they introduced. Then I'll talk about in-band full duplex IAB, integrated access and backhaul transceiver design and some simulation results. And then I will briefly mention about integrated sensing and communication and transceiver design, etc. So I think we have talked about this one in the first day. In 5G, there are three scenarios. One is enhanced mobile broadband service. The enhanced mobile broadband service is achieved by using massive MIMO technology, and then massive machine type communication. And this future of 5G is still not very much deployed. I think they will be maybe deploying currently at the first 5G deployment. They only consider enhanced mobile broadband service with the 5G massive MIMO technology. Still, the massive machine type communication is still using at the early stage. They use the narrowband IoT, etc., which is the 4G technology. The 5G machine type communication is maybe happening now. And the ultra reliable low latency also is not deployed at the beginning of 5G deployment, maybe happening now. Okay, so so the 6G I already mentioned this this enhanced mobile broadband is further enhanced to terabits per second service. Massive machine type communication also enhanced to accommodate more devices are connected into particular geographical area, and the ultra reliable low latency also reduce the latency from 1 millisecond to 0.1 millisecond. And then the sensing, the future base station in 6G, they not only communicate, they also do sensing the environment. So they, the previously sensing is used by radar system, and they also need a spectrum. And then our base station also need a spectrum for communication. So, so this radar system and the communication systems are fighting for spectrum. So now in the future, we like to see the radar sensing and the communications are integrated together, share the spectrum efficiently. So that's the plan for 6G. So sensing and communication are integrated together. And we also will see the AI, artificial intelligence and machine learning play a crucial role in the 6G network. So yeah, so that's I already mentioned all these things in the first day as well. So anyway, so the 6G have 6 pillars: native AI, 6G hardwares, and the software will be supported by artificial intelligence, which enable intelligent end-to-end communication links and distributed learning. The challenge here is to reduce the computational and communication cost, training overhead, etc. Network sensing, as I said, in 6G era, radar systems are expected to be integrated with the communication system to achieve a single advanced system called integrated access and backward system, okay? Integrated access and integrated sensing and communication, okay? So the radar system use need a spectrum, and our communication system also need a spectrum. They are currently disjoint system. We like to bring together and share the spectrum and the hardware and etc. efficiently rather than two separate hardware, two separate systems. So that's the plan in 6G, okay? In 6G era, radar system are expected to be integrated with the communication system to achieve a single advanced system called the integrated sensing and communication. So there are a lot of research is going on in the integrated sensing and communication. So that may be one of the topic. If you wanted to do PhD, you can have a look at it. Extreme connectivity, peak data rate of 1 terabits per second we expect to deliver in the 6G. The latency is reduced to 0.1 millisecond. Network capacity of 10 million devices are connected in 1 kilometer per square. That's the objective of the 6G. And another objective is integrated terrestrial and non-terrestrial network. I told you before as well, to provide 100% Earth coverage, we need to integrate terrestrial and non-terrestrial network. The terrestrial network is the current, our 5G system. Non-terrestrial network is the satellite system, etc. So 6G will make the unconnected in 5G will be connected in 6G. So whatever is not connected in 5G, the objective is to connect them in 6G. So yeah, and VLEO is mean very low orbit satellite, VLEO satellite. So this kind of a constellation, if you put them around the Earth, we will be able to provide service. The current LEO satellites are very, very far away. So then it's take low, there cause a latency issue. So we need to put a satellite constellation very close to the Earth. So that's called VLEO to reduce latency compared to satellite com, okay? So if you put a very VLEO networks, they also increase the coverage and localization accuracy as well. And the trustworthiness and the security is another issue in the 6G, and the sustainability and the green network design is also another challenge. So these are the 6 pillars of 6 area the people are working on. This view of 6 pillar is Huawei view actually. This is a Huawei point of view. These are the 6 view they introduce. It's a bit different than the one I talk on Monday morning, which is IMT 2030 view. This is Huawei's view. Okay, so I'm going to talk about the in-band full duplex communication. So what is in-band full duplex communication? Okay, so that's what I'm going to explain to you. Okay, so currently all the commercial communication system are operating in the half duplex mode. I told you about that yesterday as well. Half duplex mode is the one currently all the communication system are operating. That means the uplink and the downlink are communicated orthonormal fashion. One is TDD, other one is FDD. So these are the 2 fashion uplink and communications are happening. So let's talk about the half duplex communication. So here, this diagram, I'm showing a base station. So even though I'm putting some of the antennas here, they are receiving the signal. Some of the antenna here, they are transmitting, but they can be the same antenna, okay? So, but for the explanation, to make things easy, I put some of the antenna here they are receiving, some of the antenna they are transmitting, but they can be a same antenna, okay? So there are some uplink mobile users wanted to communicate to the base station. The base station also wanted to communicate downlink, some of the downlink users. So what is, so there are 2 mode, TDD and FDD mode. I told you they are uplink and downlink is happening orthonormal fashion, okay? So currently, all the system operate in half duplex mode. Uplink and downlink operate orthonormal channel. The time division duplex and frequency division duplex. So uplink can happen in a different time, but the same frequency, but downlink can happen different time at the same frequency as well. So that is called TDD. And uplink can happen, downlink can happen simultaneously, but different frequency. That is going to be FDD. But full duplex mean we need to do uplink and communication same time and same frequency. That will double the spectral efficiency. So that's the objective. So it's not easy to implement. That's what I'm going to tell you the story. Okay. So you can see here. The uplink, so I'm going to explain about the TDD system. Uplink is happening at time 1, but use same frequency, and the downlink is happening at time 2. So this is TDD, okay? They use same bandwidth, but different time, okay? So that's the TDD. So this is a time division duplex. The uplink happening at particular time, the downlink happening a particular time, but all the full frequency is used for uplink and the downlink. So this is the TDD system. So you can immediately see the waste time resources, because we wanted to use all the time for uplink, all the time for downlink, all the frequency for both as well. So if we do that, we can double the spectral efficiency compared to TDD system. Another wasted time resources and switching interval between uplink and downlink. So there's a wastage of resources as well. So let's talk about FDD. So FDD, uplink and downlink is transmitting at the same time, but different frequencies. They are here F1 and here F2, different frequency. So it is going to be like that. You know, your frequency is divided, and some of them for uplink, some of them downlink. Again, you can see a waste of frequency resources. There's a guard interval as well. We like to use uplink and downlink and same time and same frequency. So that is the objective of full duplex. So in-band full duplex communication, we do uplink and downlink, same time, same frequency. So that's the plan. So if we do that, there is a two big problem. That's why currently there's no full duplex system is deployed. So what is that two problem? What happened is there is a self-interference. So if you transmit same time here, same frequency, and you also listen same time, same frequency, there is a self-interference. When you transmit, you will transmit at very, very high power to downlink users. You are also listening from the uplink users. So this transmitted signal will cause interference here because you are transmitting same time and same frequency. So this is kind of an analog to, you know, you are shouting and you are also trying to listen somebody's whispering. So it's like that, okay? So because you are transmitting mean you are shouting, and also you are listening somebody's whispering. This is because this is coming from very, very low signal to noise ratio. So, so that's the, that is cause problem. So there is a self-interference, then you need to cancel. So if you cancel this self-interference, that you are the one transmitting, you know what is transmitted, but you will be able to, if you are able to cancel that self-interference, normally that self-interference is around 120 dB or something like that. It's a huge self-interference. So if you can cancel that, then you can transmit and receive same time, same frequency. You can double the spectral efficiency compared to half duplex system. So another challenge is the, you know, if these two guys are transmitting and listening same time, there is a co-channel interference between uplink and downlink users as well. So because of these two interference, there is currently no full duplex system is deployed so far, and this is, you know, these two challenges can be addressed, and in 3GPP, the IAB scenario, integrated access and backhaul, scenario, 3GPP mentioned full duplex can be a potential candidate. So what is integrated access backhaul is, I told you there is a IAB node, integrated access node here, and there's a base station here, G node B, and it will send information to this guy because we need, for the millimeter wave frequency, we need to extend the coverage by using IAB node here, and these guys will serve users here. So the integrated access backhaul mean this is doing access, this guy, and also listening data from the backhaul as well. So these both are wireless, So this is ideally suited for full duplex. You can transmit and you can also receive. So this guy can operate in-band full duplex mode. Okay, so that's what 3GPP mentioned. Potential application of in-band full duplex is integrated access and backhaul. Okay, so this guy is called IAB node. It will serve the users. It's kind of a millimeter wave coverage extension relay kind of node, and it's also connected to the IAB donor. We call G node B or IAB donor or base station, whatever we can call, and that will give access to this data to this IAB node, wireless access. They are not wireline. So yeah, so we can use an integrated full duplex technology here. Okay, so anyway, so let's talk about the remaining next half an hour is I will be talking about how to cancel this self-interference. Okay, this self-interference is like a 120 dB different dB strong. We need to cancel. Okay, node transmit and receive simultaneously on the same frequency, time, and slot, and up to twice the throughput. No additional transit power or bandwidth, no waste of time or frequency resources. Okay, so full duplex is happening like this. Okay, you are using the same bandwidth, same time for transmit and receiver. Okay, but the fundamental challenge is the high self-interference cancellation. Signal emitted from the transmitter, this guy's antenna node is receive its own receive antenna. Okay. And because of this, because of the large interference, what happened is it will, you can immediately think, I am the one transmitting signal here. I know what I am transmitting. So if we, from here receive signal, if I subtract this whatever I transmitted, then then I will be able to receive this one. That's intuition that you will see. I know what is transmitted. If I subtract it from the received signal, the self-interference is cancelled. But it is not that easy because of this larger power that you are transmitting, that will saturate your receiver. Okay, so saturate the front end of the receiver and simple subtraction concept cannot be applied here. So that's what I'm going to show you. Any question? Yeah. Yeah.
So the user is same. The user is only one. There is not you only get back.
For example, in the cellular system, some of the users are sending information, some of the users are receiving information. Oh, yeah. Yeah, yeah.
So I am using a full duplex channel.
You are transmitting. Okay, yes. In that case, yeah.
So in that case, how you subtract this powerful signal from weak signal?
Yeah, yeah. That's what I'm going to explain to you. Yeah, yeah. So so here, this guy is the full duplex. These guys are still, we thought we are treating these users as a half duplex system. Okay. Yeah, yeah. So only the base station is the full duplex. Okay. Okay. Because you need a strong signal processing techniques need to be applied. So base station is the one full duplex. Okay. Okay. So some example scenario for in-band full duplex. So here is the kind of a full duplex base station. is receiving signal from here. It is also, okay, receiving signal from here. It is transmitting here. Here it's like this, okay? So it's this guy is a half duplex. So these are transmitting, this guy is receiving, and this guy also transmitting to this user. So this is a full duplex uplink and downlink cellular system. And here is the, both are full duplex. Here is the both are full duplex, maybe a point-to-point IoT device or device-to-device network, okay? So here is the self-interference. This own transmitted signal is going to the receiver. This is a self-interference, and this is a self-interference, okay? The blue signal is self-interference. The black one is signal of interest, okay? So, so let's talk about this self-interference. This self-interference from the own transmit antenna to receive antenna is very strong compared to signal of interest. So signal of interest is this guy. This guy is a signal of interest. This is a self-interference. So the self-interference is very strong compared to this signal of interest. So for this guy, this is the signal he wanted to receive, but this is the interference because of this guy is transmitting to somewhere else, okay? So that's the self-interference. So it's around 80 dB or maybe 120 dB, etc. Solution in theory, the interference, this interference signal is known, as I said, already, this transmitted signal, same node is transmitting, so the interference signal is known here. The Song interference dominated regime, the channel estimate, if we can estimate this channel, we can subtract from the received signal. That is the intuitive solution, but that is not going to work. I will show you in a minute because the strong self-interference will saturate this receiver and the receiver is unable to receive the desired signal. So, yeah. So this is the normal transmitter and receiver chain here. So, so I will explain to you in a minute. So the self-interference will come here. We do an analog to digital converter at this point. And before the analog to digital converter, we need to cancel this self-interference, most of the self-interference, because after analog to digital converter, things are become difficult, okay? So let's talk about it, okay? So here is the receive signal here the receive signal here consists of this desired signal, the black signal, and the self-interference signal, okay, the blue signal. So the black signal is, here because this user is very far away, so this is very, very weak signal. So that's why the black signal is very, very weak. The self-interference is very strong signal. The blue signal is very strong, and black plus blue will give you the red signal. Okay, the red signal, the receive signal at this point is red signal, which consists of this black signal and the blue signal as well. So the blue signal is the self-interference that we need to cancel. We need to cancel, and we need to then, if we cancel properly, we can extract the black signal. So as I said, we need to cancel this self-interference before we do analog to digital conversion. So after quantization, you will get this kind of signal, and if you subtract after removing the interference, okay, after removing this blue signal, what you are getting is kind of a quantization noise, okay? If you do it in the digital domain, after you do the after quantization and after removing that interference, what you will get is a quantization noise, and from this guy you won't be able to Why the battery is dying very quickly? Okay, we can continue. So the after you do analog to digital conversion or after quantization, if you remove this signal, this blue signal, and then you will get this signal which is hopefully the corresponding to this signal, but from this one you won't be able to decode because this is just a quantization noise, okay. So after analog to digital converter, the desired signal saturate, get only 1 to 2 bits of resolution, cannot be decoded, okay. Usually the receiver need at least 6 bit of resolution. Okay, so this intuition of what are the signal that we transmitted, we know. Why don't you subtract at the digital domain? This kind of self-interference cancellation is not going to work. Okay. So in real life implementation, strong self-interference must be mitigated in analog domain before analog to digital conversion. Okay, before the analog to so we need to cancel this self-interference before we do analog to digital conversion. So we will do some kind of antenna cancellation, analog cancellation, etc. Then we will reduce the self-interference as low as possible. Then we do the remaining self-interference in the digital domain. So we need to bring the self-interference below the saturation region of the receiver. So that's what, to do that, we need to do analog domain cancellation before the analog to digital converter. How much interference need to be canceled, how to cancel. So, okay. So let's consider 2 scenarios. So I would like to explain 2 scenarios and tell you how much self-interference that we need to cancel. So let's say there are 2 scenarios, small cell scenario and Wi-Fi scenario. So 2 scenario here. This is the transmit power 20 dBm and in the small cell scenarios, and the Wi-Fi scenario also, let's say 20 dBm. Okay, and the power of the receive self-interference. This self-interference is let's say here is 5 dBm, and the Wi-Fi also 5 dBm. Okay, and noise flow. Let's say the noise flow here is in the small cell scenario minus 100 dBm. Here is minus 90 dBm. Okay, so let's the signal. This signal of interest is very this user is very far away. So this signal will be minus 80 dBm, and here also minus 80 dBm. So what we need to do is we need to bring this guy, this self-interference, below the noise flow. Okay, we need to cancel. This is 5 dBm. This is minus 100 dBm. So we need to cancel almost 105 dBm cancellation. Bring this self-interference below the noise flow. Similarly, we need to bring this guy below the noise flow. So that's the. If we do that, we can enjoy the in-band full duplex benefit. Okay, so we need to cancel here 105 dB required cancellation to bring the self-interference down to the noise floor. Okay, similarly here in this scenario, Wi-Fi scenario, if we use full duplex, we need to bring this self-interference 95 dB self-interference cancellation we need to do to bring the self-interference below the noise floor. Okay, if we don't do that, what happened to if we don't do that, our signal to interference plus noise ratio is minus 85 dB, and you cannot communicate at minus 85 dB any communication. So without self-interference cancellation, the signal to interference plus noise ratio is minus 85 dB. With minus 85 dB, you cannot do any communication at all. So here is also, if you don't cancel it, your signal to interference plus noise ratio is minus 85 dB. So we need to cancel. So receiver in-band full duplex system useless such a SANR. This SANR is useless, and this is called self-interference dominated over noise. Okay, but if we can cancel the self-interference, okay, if we can cancel the self-interference here, if we can cancel the self-interference and bring it to noise flow, similarly, if we can cancel the self-interference and bring it to the noise flow, then we end up with noise dominated over self-interference and signal to, if we can cancel it, the signal to interference plus noise ratio is about 20 dB. So this is a good signal to interference plus noise ratio, and you can do communication. Okay. Similarly here, if you can cancel the self-interference more than 95 dB, your signal to interference plus noise ratio is 10 dB. 10 dB is a good signal to interference plus noise ratio for communication. So yeah, so you can see in the small cell scenario, we need to cancel this guy 105 dB, and here is 95 dB we need to cancel. So we cannot use a particular technology only to cancel this one. We are going to use 3 technology here. One is antenna cancellation, analog cancellation, and the digital cancellation. 3 way of cancel, 20 dB, 30 dB by antenna cancellation, another 20, 30 dB by analog cancellation, the remaining 30 dB by digital cancellation. So we do a 3-domain cancellation. Okay. So large amount of self-interference cancellation required to mitigate the SI to below the noise flow. Small cell scenario, more than 105 dB SI cancellation is required. The Wi-Fi scenario, more than 95 dB of SI cancellation is required. With the network densification, I talk about network densification is one of the technology in the 5G to bring the base station closer to the user. If you do a network densification, then you can transmit less power compared to the original power. If you transmit less power, your self-interference also will be reduced as well. So that is another advantage. If you do a network densification, the transmitter power will be reduced, so the self-interference also reduced, so the cancellation load will be reduced. Okay, so the gain of full duplex over half duplex depends on amount of self-interference cancellation. So if we can cancel only, we will enjoy the double the spectral efficiency benefit. If we don't cancel it, then half duplex is better than the full duplex. That's why so far the half duplex is the one deployed all the communication system. Okay. But hope to see a in-band full duplex communication in 6G is some of the application like this IAB. Okay, so we did a project with Huawei doing millimeter wave IAB network to cancel this self-interference cancellation project before. Anyway, so here is the kind of a in-band full duplex terminal here. You can see here, this is the transmitted bit here. Transmitted data is going here, and it is transmitted to some users here. And so the self-interference, this transmitted signal is going to receive here your own receiver. There will be a direct path coming here, and also it will be some reflected path also going to come here. So we need to cancel everything together. These redded signal are self-interference. There will be a direct path. Maybe we can cancel it by putting some some absorbing material or some kind of beam forming, etc. we can do to stop the direct path. But there will be some reflected path also going to come and cause self-interference as well. So yeah, so that's the problem of this self-interference cancellation. So I talk about, so this you can do some absorbed material can be put between transmitter and receiver, etc. to stop some direct path. Also, you can do some transmit beam forming such that that radiated energy is not going in this direction, etc. So this is kind of an antenna kind of cancellation. Okay, there's another analog cancellation. There's a circuit here, analog cancellation circuit. What is this circuit is doing is they taking the signal from here before the transmitted signal antenna, and then it will mimic this self-interference channel is created here and then subtracted before analog to digital conversion. So before analog to digital conversion, we need to cancel as much as self-interference as possible. We do it in the antenna domain, we do some absorption material in between, and we do some analog cancellation before analog to digital conversion, etc., such that the strong self-interference won't be saturate this receiver. Okay, if we don't do this self-interference cancellation, this receiver will be saturated because it's a strong signal, and then you don't have, you cannot do anything. So so we need to cancel all these interference, antenna domain, analog domain, such that the strong self-interference is not going to saturate this receiver. Okay, so we need to cancel in propagation domain or in the antenna domain. Analog circuit, this is the analog circuit cancellation. You take the signal here and mimic the self-interference channel here and subtract before analog to digital conversion. This is analog cancellation. And then the remaining will be deal with the digital domain. Okay, the remaining residual self-interference we can do cancel at the digital domain. So this is the kind of a, so we do, let's say, 30 dB cancellation here, another 30 dB cancellation here, and remaining 30 dB or 40 dB cancellation there. If you do it, then you can enjoy the full duplex benefit. Any question? So that's the plan. So combination of antenna cancellation, analog cancellation, and digital cancellation will lead to this 110 dB or 105 dB cancellation. So people have demonstrated this one. By doing so, you will be able to cancel the self-interference and able to enjoy the full duplex benefit of doubling the spectral efficiency. Okay, doubling the spectral efficiency is a huge benefit. You know, some early work people consider, you know, there's one transmit antenna here at distant D. This is the receive antenna. If you put another transmit antenna plus D plus lambda over 2, then the signal will be, add destructively because these are lambda over 2 different. So this signal here will be destructively add together, and one kind of a cancellation can be possible. People have done many way of cancelling antenna cancellation. Okay, so anyway, two transmit signal. The two transmit signal, this signal and this signal, interfere destructively at the receiver to cancel, so the interference will be reduced. So this kind of techniques people have studied. Here is another technique. So this is called a balloon transformer. What this will do is it will take the receive signal here and mimic the self-interference channel here by finding the attenuation and delay of the self-interference channel, and then subtract from the receive signal to cancel in the analog domain before it is changed to analog to digital conversion. So yeah, so you need to cancel majority of the self-interference before analog to digital conversion. So this is a kind of another analog cancellation, okay, analog cancellation techniques. Okay, so the remaining, if we do both analog and antenna domain cancellation, the remaining cancellation, you do it in the digital domain. So the digital interference cancellation, you can do it at the digital domain. Any question? So the residual self-interference, so after analog and antenna cancellation, the remaining residual self-interference will be handled in the digital domain. So that's what is shown here. The residual self-interference around 30 to 40 dB still exists that can be done in the digital domain. So depending on the strength of the residual self-interference, optimum transmitted strategy for half duplex system can be far from the optimum in-band full duplex system. The residual self-interference is not well handled. It is still prevent us from benefiting. So the residual self-interference is still we need to properly handle and eliminate, then only we can enjoy the in-band full duplex benefit. Okay, we can do many techniques to handle that residual self-interference by using beamforming, power allocation, etc. So next is self-interference cancellation techniques. Okay, so this is kind of a recap. I think you know all these things. Okay, so this is the kind of the power budget for in-band full duplex node. Okay, so here the signal of interest is this guy, and this is a strong self-interference, and this is a co-channel interference. Okay, so you can see here this is the transmitted power from the transmit antenna, and you cancel some of the self-interference in the propagation domain. Okay. Then you cancel the remaining self-interference in analog domain. Okay, so this is the cancellation in propagation domain. This is the cancellation in analog domain. Then your self-interference is going to come somewhere here, and the receiver dynamic range. The receiver dynamic range is here. So what you had to do is you need to bring the self-interference cancellation, self-interference signal below the dynamic range of the receiver. Then the receiver won't be saturated. So, so you need to bring the self-interference within the dynamic range of the receiver. So by doing propagation domain cancellation, analog domain cancellation, you bring it to here. So this is here. This is okay. If you bring it here, that is in the dynamic range of the receiver, then it won't saturate your receiver, and you can deal with the digital domain cancellation, etc. So here is the self-interference signal. This is a signal of interest here. Okay, this is the self-interference in dB, and this is the self-interference minus propagation domain cancellation. You are here, and then you do antenna analog cancellation. You are here, and then you need to do digital cancellation. So here I show you some noise flows. Okay, the receiver noise flow depends on the bandwidth. If you are using 10 megahertz channel, your receiver noise flow is minus 1 dBm, 91 dBm. If you increase the bandwidth to 400 megahertz channel, if you are in millimeter wave frequency, your 5G millimeter wave frequency can have a 400 megahertz channel. In that case, your noise flow is minus 75 dBm. Okay, so yeah, so if you do analog propagation, analog domain cancellation, you are here. Then remaining you do in the digital domain to cancel to bring it here. Then you will be able to detect the signal of interest. Okay, so that's this is a kind of explaining the power budget. Any question? Any question? Yeah. Okay. Yeah, so self-interference must be suppressed analog and antenna domain to bring it here in the dynamic range of the receiver. Otherwise, it will saturate the receiver. Okay, so people have done many research in this topic. Okay, review of self-interference cancellation techniques. People have done propagation domain cancellation. There are passive methods, there are active methods. Analog domain cancellation also people have done in time domain, frequency domain. I'll tell you about some photonic assisted analog cancellation in a minute, and some then the digital domain cancellation, we can use linear techniques, nonlinear techniques, and some receiver beamforming techniques, etc. Okay, so there are many research have been done to do this self-interference cancellation in all these domains. So, so here is some example here. You know, the interference in propagation domain mainly focus on minimizing the direct path. For example, this is the transmit antenna, this is the receive antenna. You can put some absorbed material here to stop this direct path from going from here to here. So this can be done. Okay, so this is mainly to stop the direct path. And then there are some active approaches. This is the circulator that I was telling. The circulator I put here the two antennas, but it can be one antenna. The transmitted signal will go here in this way, and the receiver will go this way. So same antenna will do transmitter and receiver by a technique called circulator here. So anyway, so and then the transmit beamforming, also another techniques. This is the self-interference channel. You transmit orthogonal to the self-interference channel or in the null space of the self-interference channel. By doing so, you won't cause that much of self-interference as well. So there are many, there are a few techniques people have done to cancel as much as self-interference, okay? So transmit beamforming will be steer the beam to the narrow direction towards the intended node, reduce the self-interference, okay? Or it can also steer the beam to the null space of the self-interference channel to null the self-interference. So yeah, so there are, I will tell you about a little bit of this null space projection techniques, etc. Later on. So, so transmit beamforming is the one I'm going to tell you now. So we can do a transmit beamforming, the one I'm mentioned here, transmit beamforming or null space projection, etc. So what you do is you find a beamformer matrix V, which minimize this. This is the self-interference channel HSI, and V is the kind of a precoder or beamforming matrix. So you find a V that minimize this H into V. Okay, so this is the kind of a it's called a null space projection techniques. Okay, so you transmit in the null space of the self-interference channel. Okay, so step one is to find the desired beamforming matrix to minimize the mean square error, MMSE. So this is the error of from the downlink users, and this is the error due to uplink users. So you sum both of these error and minimize these both of the error with respect to this V, the precoder, and then you find the precoder, and then then do some further processing and try to find the null space beamforming techniques. Okay. So we have kind of extend that techniques to a little bit further by putting how much self-interference that we need to cancel by putting some threshold here. So this is the some reduced complex beamforming techniques that we have proposed. So we have shown here, so this is the spectral efficiency versus analog self-interference cancellation. So this is the kind of a null space projection techniques people have used, and we have proposed some other techniques here which is performing better compared to the null space projection techniques. So yeah, so this is four users. Here users have two antennas, and here users have four antennas as well. So yeah, so these are the our studies of cancelling the self-interference by beamforming techniques. Any question? I think it's going to. I think that's all I wanted to say about. I'll skip this one. Okay, so I'll explain this one. So there are two architectures that people have proposed to cancel the analog domain self-interference. This is the techniques that people proposed at the Stanford University. What they did is they take the signal from here, and this is your self-interference channel, okay? And then they create this self-interference channel and then subtract from the received signal, receive RF chain, and they subtract it here. So this is the self-interference channel, including the reflected path, etc. That it will create it, and then it take the signal from the transmitted signal, and this is a self-interference channel, and then multiply that, and they get self-interference is subtracted before analog to digital conversion. So there's another group at Rice University. They propose some different architecture. They take the received signal, they come up with the auxiliary RF chain and some DSP that will mimic the self-interference channel, and then they cancel it here. I think we follow this architecture, and in the Huawei project that I mentioned, we need to cancel self-interference for bigger bandwidth, like a 400 megahertz channel, because of the millimeter wave frequency. We come up with the techniques called optical domain cancellation. So because if you have a 400 megahertz channel, the channel is more frequency selective. There will be more taps and etc. is needed. So if we do this kind of microstrip based analog cancellation circuit, we won't be able to create a multiple tap channel. So what we did is we take this electrical signal and convert the electrical signal to optical domain, and we create this self-interference channel in optical domain. In optical domain, the losses are less, so we can have a multiple taps, etc. A large number of taps, like 80 taps, etc., can be created, and do the cancellation, and then change the optical signal back to electrical signal, and then cancel the self-interference. So that kind of techniques that we proposed. So you can some plot here. It is cancellation performance versus tap, okay, for 70 nanosecond delay spread channel here. These different lines are for different bandwidth. So you can hear this is the 1 gig bandwidth channel. To cancel a reasonable amount of self-interference around, let's say, 30 dB, you need to have a lot of taps, okay, a lot of taps, 80 to 90 taps. So that kind of many taps cannot be created in the microstrip-based circuit. So we need to do kind of optical domain cancellation. So similarly, for example, the Jello is a 400 megahertz channel. To cancel like 40 dB analog cancellation, you need to have a 70 or 80, 90 taps. So that kind of many taps you cannot create in the microstrip-based analog cancellation. So that's the kind of a study here showing. This is bandwidth is 400 megahertz channel, but different delay spread are shown here. Again, if you have a larger delay spread, you need more taps, etc. So, I'll show you. This is our electrical domain, optical domain 5-way array based cancellation. We are taking the received signal, tap the received signal, and change it to optical domain, and we are creating a different delays and attenuation, and making this is our frequency selective channel with many taps, and then we change the optical signal to electrical signal and then cancel it, okay? So Yeah, so this is one thing. And there's another techniques people used before as well. It's called fiber brigade based cancellation. Again, you know, the transmitted electrical signal is taken and then converted to optical domain with the different tabs here, and make the analog you know, self-indifferent channel using optical domain, and then cancel all these things and get the you know, electrical signal back here and subtract it here. Okay, so here the electrical signal is converted to optical domain and create the multi-type channel here, self-interference channel, and change it to electrical signal and cancel it at the receive antenna. So this is the one creating the you know, self-interference channel with a lot of tabs that is needed in the higher bandwidth case. So this is kind of the lab we have done this kind of experimental work. This is funded by Huawei projects. So any question? I think I hope I explained to you about the full duplex benefits and the challenges of canceling the self-interference, and we need to cancel in 3 domain, analog antenna and digital domain. If we can cancel properly to bring the self-interference below the noise floor, we will be able to enjoy the in-band full duplex benefit of doubling the spectral efficiency. I think that's all I would like to say. Yeah, this is kind of a, this is a circuit here. For example, this transmitter antenna sending information to the user. That information is going to the receiver. This receiver can be a same antenna, but it can be different antennas as well. So this is the self-interference that we need to cancel. This is the receiver is receiving a signal from here. So the self-interference have a direct path and also some multiple reflected path. So this self-interference channel is created here in the RF canceller and then subtracted, and before we change it to digital analog to digital conversion. After that, you do the remaining self-interference, you do it in the digital domain. Again, so you know, you need to cancel the self-interferent analog domain in an appropriate level. For example, this is a self-interferent channel, the signal, and this is the noise floor. You need to, here, if you this is a self-interference cancellation done from here to here. That is insufficient cancellation. And you also shouldn't cancel too much as well. If you cancel too much, then what happens is the digital domain cancellation become a problem. So you need to cancel the self-interference appropriate level such that the remaining self-interference will be canceled in digital domain. If you cancel more, you are unable to estimate the channel for self-interference channel properly, then you cannot do much on the digital domain. So you need to cancel appropriate level. So here is a too deep cancellation. You can cancel from here to here. That is too deep cancellation. Here is too less cancellation, and this is kind of appropriate level of cancellation. You bring it to this maximum tolerable strength. If you cancel up to maximum tolerable strength, the remaining can be dealt with in the digital domain. So there are a lot of technical details are there, okay? Yeah, so I explained to you this integrated access and backhaul is a nice application of in-band full duplex. So for example, in 3GPP, they introduce a scenario called mobile IAB. What does that mean is in the railway compartment there will be a access point, IAB node, something like that. It is going to move the train when the train is moving. There is a donor or base station will give access to this IAB node, wireless access through wireless link, and then this access point will serve the users inside. This is a kind of a scenario for mobile IAB network. So this guy can use full duplex technology because this guy can serve the user and same resources, frequency and time resources can be used for backhaul with the base station to get the data as well. So this is kind of a ideal scenario for in-band full duplex. So same resources is used in backhaul and used in the access. Okay, so this is called access. It's serving the user, and it will also connect it to the base station through wireless backhauling. So the same frequency time resources used for backhaul and access by using in-band full duplex. So this kind of nice scenarios for in-band full duplex. And anyway, I think I will stop here.
Yes, sir, TKM.
Yeah, TKM. Yeah.
At what time you want them to come, sir?
Half an hour break, I think.
Half an hour.
Yeah.
After half an hour, then, sir. Yeah, please come back at 11:20.
The simulation, this E1 in this section 2, where this P is in -525 dB, and this is the multi-user MIMO simulation. This is the rate for each user. There are two type of beamforming, MRT and ZF. We choose n equals to k equals to 4, n equals to number of antenna at the base station, k equals to number of users, and we compare three things: MRT, ZF, and single user MIMO with water filling. Okay. So here we are. So here we have defined these parameters. So here what I did, I have changed the SINR, this transmit power from -5 to 30 dB to see for longer range. Okay. We have n equals to 8. We can choose n equals to 4 as well. Then k equals to 4. NH I have taken, NH is the number of channel realization. Okay. So whenever in the paper we present result, we average for the more number of channel realization. Okay. So here I have chosen 1, so that program run quickly, otherwise it will take longer time. Okay. And for each initialization, each channel realization, I choose the value of H here like this. Okay. So let's run this and see up to here. We have F10, 4 cross 4. Go next. So P is the first value, 0.36, and this is the MRT. This is the normalization. Then we check the value. So these are the value you see. So diagonal value represent the desired signal, and off diagonal value represent the interferences. So example, this first row represent the first desired signal, and these 0.27, 0.11 and 0.37 are the interference power at the first receiver. Okay. Similarly, here in the second row, the first term, the third term and the fourth term represent the interference power at the second user, and this 0.86 is the desired signal power at the second user. Okay. And R is the multi-user rate. Okay. We can also go inside and see what is happening there. Open. Okay. So here is the same thing, Rk equals to log 2 1 plus numerator divided by denominator. I am running the loop for all user, and numerator is hk transpose fk. So I have multiplied hf already here. Okay. So I don't have to multiply again and again, and here I have to take the summation for all j minus k. So this summation, so hk Hermitian fk. So this hk and fk is multiplied multiple times. So I multiplied here all of them at once and take the element one by one. Okay. And we are talking about the kth user. So k comma 1 to k minus 1, k plus 1 to up to k. So it means I am excluding the kth entry. Okay. So this will give me this part. Okay. Where this p and this normalization is already included in f. Okay. So p is here and normalization is already in f. Okay. So normalization is already in f here. So that way I can calculate the rate. So we have 4 user. So this R will be a 4 cross 1 vector, 1 cross 4 vector. Okay. So here we take the sum and store this for each channel realization, each value of the transmit power and the first entry here. Similarly, we can do for zero forcing. We have the same expression with normalization. We can also multiply power and write 1 here, or we can write power p here, write 1 here. We can do both ways. Okay. You have to multiply only one place, and this is the absolute hf square, the power here. So you see here interference is 0. Okay. So at the first receiver I am only getting the desired signal, rest of the terms are 0. Similarly, at the second user I have this 0.1304 and rest of the terms are 0. Okay. So this is the zero forcing. So next I calculate the rate here, and this is the same thing as water filling. So yesterday code was not running due to VAC function. Okay. VAC is a vectorization function defined in the CVX, but there is already a new VAC function introduced in MATLAB 2024. That's why it was not running. So this is my older MATLAB 2023A. So it will run. So here what I am doing here, I am generating this eigenvalue. Earlier yesterday I have written here sigma square, right? That same thing, and this noise power is 1 here, and I defined the rate function, and I did the water filling. Water filling is the same program here. Okay. SNR log 1 plus SNR subject to the power constraint. Okay. Simple CVX program. Okay. So it will give me some values for power allocation. Okay. So it is giving me that I can allocate power like this, I will get the maximum rate. Okay. So this is at the low SNR. Okay. So these are the rates at first value of the transmit power. Okay. So I can run this loop. So let me remove this debug point and run, continue. It will give me all possible. So here you see for zero forcing interference is 0 every time. Okay. As the SNR increases, these value increases. Okay. So here it is going 10 to the power 3 into 1.74. Okay. So here you see here MRT, initially it is giving little bit better, and after that it saturates due to interference. Okay. and these MIMO water filling and this ZF only have a constant gap. So constant gap means it will achieve the multiplexing gain. Okay. Constant gap you can fill using the little bit by increasing the transmit power. Okay. So constant gap is okay if you are achieving constant gap when doing the power scaling. So it sure it will achieve the multiplexing gain at high SNR. The slope of this and slope of these are same. Okay. So now if we increase the value of the number of transmit antenna at base station, this these MRT terms, these term will go to 0. Okay. And this curve will shift upward. Okay. So there will be still some saturation, but it will go. So let's say if I choose 128 here, what will happen? So you see these values are going almost 0, okay, compared to this. This is for 0 forcing, and these values are going 0 compared to 33. These are very, very low. Okay, so these interference term are going very, very low. Okay. Since dimension is large, it is taking little bit longer to run. Okay. So you see here, this is 5,000 and this is very low compared to for example, this is 5, then this is 0.01. This is like 1/100th of it value. Okay. So this blue curve will shift little bit upward. Okay. But there will be still some saturation. Okay. So here you see 0 forcing is overlapping with this yellow line. Okay. Since I was running for only one realization, if you run for multiple realization, this gap is due to some, it will little bit close. Okay. So when we have higher number of realization, it is closing this gap. Okay. So these are the simulation for this section. Okay. So these are some subjective question you can think of and answer it. Okay. Let's go to the hybrid beamforming. So why we do hybrid beamforming? Because in massive MIMO we have many antennas. Okay. When we have many antennas, we need many RF chains. RF chain is what? RF chain is, so when you receive some signal at the antenna, this signal will be processed by low noise amplifier, then it will be down converted, then there will be ADC, and so this block of component is called the RF chain. So for each antenna you have to put these things. Okay. So let's say you have 1,000 antennas and you put 1,000 of these things. First, putting all these 1,000 things together is not easy. Okay, it's not feasible. Second thing, if you put, the cost will be more. And the third, I mean, even if we include in the cost, but third thing is the crosstalk. If you have multiple RF chain very close to each other, there is a crosstalk. It means, for example, you have two open wires, it will cause interference to other. Okay. So there is a crosstalk between them. They will interfere with each other. So you will receive some distortion, nonlinear signal. Okay. So we cannot put everything. So we cannot put every antenna connected to with RF chain. Okay. So that's why there is a hybrid beamforming. So in hybrid beamforming, what we do? So we have, let's say, 256 antenna. We will divide into panels like a subarray. So in the 256 array will be divided into subarrays. Okay. So let's say 64, we divide into 64. So there will be like 6. There will be 4 subarray. Okay, for 256 antenna. Okay. So let me draw here. So you have 256 antenna. You can divide into 4 subarray. Okay. 64, 64, 64 and 64. Okay. So you can connect this with array of 8, 8 RF chain. Okay. So it is 32, right? So 8 is 32. So we will have 32, 32, 32 each. Okay. So we will have like 8 RF chain will be connected to this. So these group of arrays, okay. So there are like 32 elements here in this planar array. So this will be connected to one RF chain. Okay. So what we do here, we perform this here RF beamforming first, then connect it to RF chain. Okay. So in the RF beamforming, what we do, whatever the signal is coming, whatever signal we are to transmit, we can change the phase of it. Okay. We can, if we do not connect it, that's also okay. It will be just doing nothing. Okay. So here what we can do, we can adjust the phases of that signal. Okay. So FRF is the beamforming we do. So this is called RF beamforming. So what we do here, so whatever the signal is coming, we can change the phase. So it is each, so FRF, this is a matrix because there are like multiple elements. So each element will be connected to here, and we can do RF beamforming. From RF beamforming, we are getting only like some signal. So we have left 32 here. Okay. So this RF beamforming for this particular block will have 32 cross 1 array. Okay. Similarly, this will have RF beamforming 32 cross 1 array. This will have 32 cross 1 array. And each element, so let's say F, RF, I comma J, its element will be, its absolute value will be 1. It means we are only providing phase shift here. Okay. So this is the thing we do, that is called RF beamforming. Okay. Just to provide additional control over the beamforming. Okay. And rest of it, this signal is coming, digital signal, that is FX. Okay. The beamformed signal from the in the digital domain, it is coming like this. Okay. So whatever signal, the scalar signal is coming here from one RF chain, it is here. Okay. So so ultimately, earlier you have equation like this, y equals to h, let's say f u plus w. Okay. So this was like your transmitted vector. Okay. So now your equation will look like this, f rf into f into u. So this is f digital. Okay. So this f is equal to FRF into FD. So this FRF, since we have this 32 array like this, so it will have like block diagonal structure. Okay. So let's say this is so this is what, 256. Okay. So here it is 256 cross. So this is k cross 1. So this will be k. So k is here, 8 here. So I am writing, let's say 8 here, and this is 8 cross 1. Okay. So this will be 256 cross 8, and this is 8 cross 8, or this is 8 cross 1. Okay. So this 256 cross 8 will have block diagonal structure. So one like this, like this, like this, and like this. Okay. And so on. So I mean it will be 0. So this is like an array. Okay. So one vector will be here, then rest of them 0. In the second row, second vector will be there, then all zeros. Okay. Then here, this is the FRF vector, this vector. So this is a 32 cross 1 vector. Okay, so this is the RF beamforming. Okay, and this part is called the subarray. Okay. Okay, na? Okay. So here here we are showing one type of FRF design here. Here we are only providing the phase shift. Okay. So let's read this first. So your situation will be very clear what we are doing here. So in the previous section, we considered a downlink scenario where the base station was equipped with a digital beamformer. In the massive MIMO scenario, however, employing digital beamforming can increase the cost and power consumption. Okay. So one way out is to use the hybrid beamforming. In hybrid beamforming, a large number of N antennas are connected to a small number of RF chain. Okay. So via a network of phase shifter to support K users, assume M equals to K, okay, number of RF chain is equal to number of users. Okay. So here 8 cross 8 is there. Okay. It means 8 user can be connected. Okay, and for the rest of this exercise, in this case, beamforming F equals to FRF into FB. So I have written here F equal to FRF into FD. D is the digital beamforming. Is performed in 2 stages. One is digital beamforming in the baseband with FB, and second is RF beamforming with the phase shifter network with FRF. Okay. So here I have divided the whole array into sub-array, and that way I will get the block diagonal structure. Okay. So if I do not want to divide the sub-array, I can connect all RF chain in one RF beamforming and connect all of them. Okay. So it means this will not be block diagonal in that case, but that structure will be complex. So this is what is explained here, that if we connect all RF chain together with all of the antenna, okay, so this matrix will be of the same size 256 cross 8, but it will not be block diagonal. Okay. There won't be any sub-array kind of concept. Okay. Do you understand? Should I repeat it again? Okay. So here FRF is not diagonal here because sub-array concept is not considered here. Okay. But in implementation, in practice, this type of concept is considered. Okay. The whole array is not taken all at once. It's very difficult to implement in practice such kind of interconnected mesh type of phase shifter network. So in this exercise, we consider 2 types of channel: uncorrelated Rayleigh fading channel (IID) and sparse geometry based channel. We assume the transmitter is equipped with a uniformly linear array. When there are L multipath components from the transmitter to each receiver, the geometry based channel matrix for the kth user is expressed like this. So this is what multipath channel. Okay. So do you know about the steering vector? Okay. Steering vector, everybody know? Okay. So this is the channel. Let me write here HK equals to summation L equals to 1 to L. L is the number of paths, and we have square root n divided by L. Then we have beta L, and we have beta KL. We are talking about the kth user, and we have this A is the steering vector, and this is phi KL. Since we are assuming single antenna at the receiver, so this will be a vector. Okay, this will be of n cross 1. Okay, and this will be of n cross 1. Okay, and this is all 1 cross 1 with CN01 entry. Okay, and phi we can choose random values uniformly distributed between 0 to pi. I think it's written there. So phi KL is between 0 to pi. Okay, you can choose uniformly. So this is how we can generate a random channel for a sparse random channel for a sparse channel. Okay. So sparse channel means when number of paths are less than number of antenna. It means there is not rich scattering. Okay. So you have this kind of signal. Okay. This is the steering vector. It is given here. Okay. So in electromagnetics, you might have read this steering vector also. Okay. So this is the steering vector, where lambda is the wavelength, phi is the this azimuth angle, and d is equals to lambda by 2. And in this following, we perform the simulation for the Rayleigh fading and sparse channel with L equals to 1 to 1050, going from lower to higher, and set the SNR region from -20 to 20, n equals to 64, in number of antenna at base station 64, and m equals to 4, number of users are 4, number of RF chain equal to 4. So define the effective channel HE equals to H into V1 to K. Okay. So what we are saying here, so we choose FRF like, so effective channel is like this. So if we take this, so this will be called as effective channel. Okay. So here we are saying, first try trivial simulation. Trivial simulation means we choose H effective channel equals to H into V 1 to K. 1 to K. So what is V? V equals to eigenvector of this singular vector for this. So H equals to U S V Hermitian. So what is the dimension for H? The dimension for H is n K cross n, right? So this is K cross n. So this will be what? K cross K, and this will be K cross n. And what is the dimension for V? Only V. So V has the dimension how much? N cross K. We are taking Hermitian here, so it will become K cross n. So it will be n cross K, right? K cross n. Okay. So here if we are saying choose 1 to K. So instead here we have n columns. So out of these n columns, choose first K columns, and that way, so this is the one way we can choose FRF matrix. Okay. So this will be our like FRF matrix, but this, it is not satisfying this constraint. Okay. Then see what will happen. Okay. If it is not satisfying this constraint, what will happen? So let's go to 3 here. Okay. So I have defined the range -20 to 20, and dB equals to will be 15, this thing, L equals to 10, number of paths, n equals to 64, K equal to 4, number of RF chain is equal to K, and H naught is the channel function. So let's see what is the channel function. In the channel function, what I am supplying? K, number of user, N, number of antenna, and L. So this is the previous value that we have run here. We have not run here. Let's run here. Okay. Let's go here and go step in here. So we come here. So now we are generating the channel using that formula. Okay. So for each user we have to generate the formula. So we initialize the matrix H equals to zeros K comma M. M is the number of antenna in this local function, and beta is the CN01 variable. Okay. So I have generated using rand-n. Okay. Then we have theta. Theta is generated between 0 to pi. So rand generate value between 0 and 1 uniformly, right? Now if I have to translate this value between 0 to pi, what I have to write? I have to write lower bound plus upper bound in minus lower bound multipliers of that into that random variable. Okay. So that's why I have written here, I am generating between 0 to pi, so lower bound is 0, then pi minus 0 rand L comma k. L comma k is what? Number of paths and number of users. Since phi kl is there, okay, and this is the steering vector I have defined here. I will provide value theta here and n here, and this is exponential j pi. So let's see here, just to remember. So we have e to the power j 2 pi d by lambda. So if we put value of d here, lambda 2 cancel, so we will remain with j pi cos theta, cos phi. Okay. So e to the power j pi cos phi. So I have assumed the th variable, and 0 to n minus 1. So this term is coming here up to 0 to n minus 1. Okay. And divide by square root of n. This is for normalization. Okay. Then for each user, we generate the channel. We initialize with 0 for each user. Okay. We are generating row channel because h is k cross n here. So we have to generate each row like this. Okay. So each row we have to generate. So I am generating. So this is the way I am writing the summation here. Okay. That summation, I am initializing with 0 and taking the summation. Then I am writing beta. Then this vector, steering vector, the same thing. Okay. The same formula, nothing fancy. Okay. So let's run this. I think it's very easy to code, not much difficult. Only you have to look out for the dimensions. Okay. So for example, here I have taken transpose here. Here I have taken transpose here, just to look out for the dimensions. Okay. So it should not give any error. Okay. So let's come back here and run up to this point. Let's delete this. Okay. So we are here. So I have taken the SVD of H naught. Okay. So step. Now I initialize the R sum here for each transmit power value. So this is my effective channel as written in the handout. Okay. And for this effective channel, I am doing the zero forcing and normalization, calculating the rate here, then summing it. Okay. Now the second thing I am doing for H naught. H naught is my original channel. So here we have to do two things. One is for HE, one is for H. Okay. So H is this thing, the original channel. Okay. So let's do this. Same normalization, same rate calculation and summation. Okay. So this part is for E2. Okay. So let's come to the E2 first also, because it will be running in the loop. Okay. So in E2, what it's saying, choose the FRF according to like this. So we have V matrix that we have generated using SVD. Take the angle and put it into the exponential j theta, and that will be FRF. Okay. And it will satisfy this constraint. Okay. Then plot the achievable rates using zero forcing. So that's what we have did here. I have put here FRF exponential j theta. So this is the V. I have taken the angle of it and put this. Okay. Then this will be my effective channel H naught into FRF, and I am doing the same zero forcing, then normalization. Now here you must take care of this transmit power constraint here. Okay. So my transmit signal includes this whole FRF into FD. Okay. So instead of just multiplying with this only digital beam forming part, you need to multiply with both. Okay. Because your F is equal to FRF multiplied by FD. Okay. So normalization you need to take care of. Otherwise, if you have different normalization, it will cause different result. Okay. You may falsely claim my results is going better. Okay. So that's not good. If somebody verify, then it's bad. Okay. Then I calculate the multi-user rate, then sum, then store. Then here I am doing the same thing, MIMO single user with water filling that I did previously. Why we are doing it? Just to check how much we are achieving for that channel. Okay, just to compare. Okay. Okay, so this program is clear. So let's run this and see. I think you already have this program, so you might have run it. So all are for zero forcing. So zero forcing should scale according to this SNR, right? So first is blue line, that is the effective channel. So with this, so here in this there was no normalization. Okay, so it will give better result obviously. Okay, and it will be close to MIMO one user. Okay, because this is the optimal. We are considering single user. So this last line and the first line will match. Okay, and second is zero forcing, simple zero forcing. So earlier it was showing some gap here, right? So this will also have very little gap, and if we run for multiple realization, this gap will close. Okay, and this is HE is equal FRF. This for FRF beamforming with this constraint. Okay, because this is not an optimal beamforming, because we are constraining F to be like this. Okay, so it will reduce a little bit. Okay, so this reduction you can see here, and this reduction is constant. Okay, so is this clear? Right? Very easy to plot. Which matrix? H matrix. FRF. So this is the FRF matrix, and each of its element is absolute value is 1. Okay. Any question in this? So without seeing this code, can you write this code by yourself? Everybody? I think it's easy. Okay. Any question in this code? Or FRF beamforming, or digital beamforming, subarray based beamforming? Okay, so subarray kind of stuff is the advanced stuff beyond the hybrid beamforming. After normal hybrid beamforming, we go for the subarray. Okay. So subarray will have diagonal structure. So presently we have this full structure, as we have see here. We have this structure. Okay, the full structure. Now if we constrain this to be diagonal, my rate will also reduce also little bit more. Okay, but its benefit is that my architecture in hardware will be simplified a lot. Okay, so that's a very small price to pay. Okay, so that's why we go for the subarray kind of structure. Okay. Any more question? Okay. Yeah, this one I think so let's read this also. What happens for the sparse? These are all subjective questions, you can answer it. What happens for the sparse channel? Compare the result with a single user scenario where SVD based transmission water filling was possible. So we have compared it. Answer the following question: when L equals to 1, L equals to 50, what are the differences between the performance of hybrid and digital beamforming? Assuming ZF used in baseband, repeat the exercise for K equals to M equals to 52. So what will happen? So we have less, when L equals to 1 means there is less scattering. Okay. So if we have L equals to 1 here, so there is less scattering. Okay, less scattering means there is a chance for correlated channel, so rates will reduce. Okay, Alec cost-effective means we have rich scattering, so there will be more rates. Okay. Comparing the multi-user scenario with single user, what is the impact of L and K? So you can play with the values of L and K. So with the L you have already seen, if we increase the value of K, it means we are increasing the RF chain. Okay. So that will lead to similar to the closer to the digital beamforming, all digital beamforming. Okay. Okay. So number of user should not exceed the number of RF chain. Okay. If we are single antenna user and they are transmitting single antenna stream. Okay. So if users have multiple antenna and they are transmitting only single data stream, that's also okay. Okay. This all depends on the rank, the overall rank of the effective channel. Okay. So for example, if we have some receive combining, the overall effective channel will include those. So the received number of streams, the total number of received stream must not exceed total number of transmitted stream. Okay. Otherwise there will be unnecessary interference. It is as simple as saying that if we transmit more with less number of antenna, less number of resources, we will not get the same thing. Okay. It's like saying the same thing. Okay. Should we finish it or go for a little bit? Okay. So are you interested in IRS or should we conclude it? IRS? So this is only very like introductory slide only. Okay. Not much in detail. Okay. So IRS you already know, intelligent reflecting surface. So I have 4 sections here. In first, so I took inspiration from Emil Jorson slide also. Okay. So we have 4 sections here. One is introduction to IRS. So I will be presenting some basic stuff. Then I have some IRS modeling. How do we model IRS? How do we use that in this kind of equation? Okay. And introduction to beyond diagonal. So this is most recent works. Okay. So how we can improve the existing IRS is given in this. So this is still in the theoretical stages. So I will just present what is in the paper. Okay. Then some conclusion. So in wireless communication we have 2 more important resources, transmit power and bandwidth, that we are managing to provide the better throughput. So power, that is transmit power, we are trying to minimize power. We have energy efficient system also, we research on energy efficiency. Bandwidth, we are putting the density closer to closer and also going to the higher bandwidth to get going to the higher frequency, millimeter wave, terahertz wave, to get the more bandwidth. Okay. So wireless channels are multipath fading channel, you already know it. Okay. And where signal is received by multiple paths. So can wireless channel be controlled? So IRS is one of the way. Okay. So IRS means intelligent reflective surface. With IRS we can control some paths. Okay. Okay. So this is one example here. So we have one mobile transmitter and we have base station and we have several buildings, and so there is a blockage also here. So blockage occurs. So blockage shows that there is no direct path here. Okay. So when there is no direct path, there will be multipaths. Okay. And this signal, let's say it cannot reach, or it is being transmitted, or it is from this building it cannot reach here. Okay. You can think of like that. But if we put the IRS block here with some IRS controller, and we can control to direct it to the base station. So in theory, or in also in the experiment, we see that even introducing one path helps very much when you do not have direct path. We also see in the simulation also. So if we introduce one more path, that is very, very helpful, okay, when direct path is not available. So IRS stands for Intelligent Reflective Surfaces. There are other names also, reconfigurable intelligent surfaces and software controlled meta surfaces. IRS can provide an extra path and strengthen the existing path between transmitter and receiver. Okay, so even if you have existing, let's say here, so there is an existing path already. If you put some IRS here, so there will be less number of less penetration and less transmission will be there, and it will be reflected more smoothly. Okay, there will be less losses in this reflection. Okay. So when there is a blockage, there is no direct path. IRS can be useful, really helpful. Okay. So usefulness of IRS depends on the path loss. So in the path loss, you already know this Friis equation from your undergraduate courses. So PR is the received signal power, PT is the transmit power, lambda is the wavelength, and DTR is the distance between transmitter and receiver. Okay, this is the Friis equation. So if you have a omnidirectional antenna, if you have a distance of 10 meter, and we are talking about the 3 gigahertz, so you will have path loss of approximately 62 dB. Okay, and if it penetrates the wall, it will cause more than 20 dB of loss. So you will receive very, very minor signal. Okay, so you have to take care. Even if we have some path, it will really helpful at the receiver. Okay, so this is one example here for the office environment or home environment. Okay, we have base station here, we have wall penetration here, we have 2 users here. So one user is receiving the signal through wall, so it will receive the attenuated signal. Okay, very, very less. And if we are receiving, we can receive one signal from IRS via some window or via some roof. Okay, so that will be really helpful, and it will strengthen this user signal. Okay, we can receive very good rates. So this is one application in a mall environment. So if we have a mall, we can put the IRS on these surfaces that can improve the indoor coverage. So where there are like many number of peoples are there. So for example, you have like lifts are also there. Its signal doesn't work because it goes underground. If you put IRS, it can create multi-part, and there's a possibility that signal will also travel there. Okay. So you can configure this accordingly. Okay. So next section is the IRS elements and their reflection coefficient. So yes, so each element needs to be controlled. Controller will be, you can put central controller or you can put individual controller. So IRS is still in the development phases. So I will show one experimental result also from one of the paper from Emil Johnson also. Okay, so controller you can put, for example, you have this, let's say CCTV cameras. Okay, so you put the wire around and put the controller at some places. So similarly, you can put there. Okay, you can connect it and put the wires around and put some controller at some central server. Okay. Yes, number of elements. Yeah, we will come to the gain. We will come to the gain, how the gain is there. So this is a real world implementation by Emil Johnson group. So what they did, so this is one panel. So in this panel, so I am showing here we have base station, we have mobile transmitter, and we have IRS panel. So this base station is transmitting and it is being reflected, and this is like a pencil beam going towards the directly to the mobile user. So how does it do? So each of its element is connected to a wireless controller. So it can change the voltage accordingly. So it will, so we have to provide phase shift. So phase shift is kind of a RC phase shift. So you, in your undergraduate courses, you might have heard of RC phase shift network, right? So that RC phase shift network, we are using the they are using the varactor diode, okay, for that. And they are changing the voltage across it so that the capacitance will change. If capacitance will change, the phase shift will change, okay. So that way we can direct the beam accordingly, okay. That is the idea here for implementation, okay. So this is, it is not shown here correctly. This part is not visible. It is visible. So can you see this part? Okay. Okay, little bit. So what I am trying to say here, okay, I will say directly. So we have this plane wave coming here, and plane wave is going out here. If we have some normal plane like a mirror, okay, and we have some tilted plane, then this wave will come here, this wave will go here directly. Plane wave. Plane wave is the input, plane wave is the output. So this is like a convex surface. So some wave is coming, it will be pointed towards this user, okay. So what we are trying to say here, IRS doesn't act as a mirror, it acts like a convex surface, okay, which can point towards a particular user or particular direction, okay. So these are the results from this paper. So these are the results for using the varactor diode for elements, so response for each element. So what does it show? They have varied the voltage between 0 to 19 across the varactor diode element, and they have seen different characteristics here. So the top curve shows the reflection coefficient versus the frequency, and the bottom shows the reflection coefficient phase versus frequency. So amplitude and phase versus frequency. So amplitude variation are smaller in the yellow band. So why they are considering yellow band? Because there is their operating frequency is 5.8 gigahertz, okay. So they will operate only here and there around the 5.8 gigahertz. So around the 5.8 gigahertz, this yellow band, they see this band, this is approximately equal to 8.8, okay. And this band, this curve is linear, almost linear, okay. So they consider only this band, like around 5.8 gigahertz. So reflection coefficients are approximately constant within this band, and thus IRS elements have approximately flat frequency response within this yellow band, okay. Almost flat they have assumed, okay. So what IRS can do, it can direct the incident, some signal that is arriving using the phase shift. It can also absorb the signal. If we can control the impedance, if we increase the impedance too much, that will put the like a resistor. It will obstacle that signal and it will absorb it, and it can also change the polarization by controlling both impedance and phase shift. So for example, these are the different kind of polarization: linear, circular, elliptical. So by changing the polarization, we can also sometimes avoid the interference also. Okay, so let's come to the modeling. Any question up to this point? Okay, so let's come to the modeling. So first we do the signal modeling. So this is very, very basic stuff that you read in the undergraduate courses. So whenever we transmit the signal, we transmit like this. So we have some signal, let's say BPSK or QPSK, whatever we want to transmit, we modulate into a pulse, PT. So let's say square pulse or raised cosine pulse or root raised cosine pulse, and shift it and transmit it. So it will make a pulse, okay, accordingly. So this pulse should satisfy the Nyquist criteria. So this is the Nyquist criteria, that is Pm divided by B. B is the bandwidth, okay. So that is the baseband bandwidth for m not equal to 0 and non-zero for otherwise. So if we receive signal can be given by like this, the convolution with that signal, okay. So at the receiver we will do some filtering. So filtering we do with the PT, so it will be given by like this, okay. There is nothing here, we just do the convolution here. So it will have two convolution here. So after that we do the sampling. So in the sampling, this is the sampling frequency 1 by B. So in the baseband, okay. So sampling theorem says, so this is this is B, so this is 0 and this is B by 2 and this is minus B by 2. So the maximum frequency content here is B by 2. So by sampling theorem, the sampling frequency must be B at least. So the sampling frequency is B here. So we are sampling here. So this should be 1 here for K equal to M, otherwise it should be 0 for the Nyquist criteria, and this is the effective noise here. So we will get some channel here and the corresponding signal, and for a narrowband channel this HT will be simple flat fading channel, only one coefficient will be there, flat fading. Okay. If you have frequency selected, there will be a multiple taps here. Okay. So next, this shows the similar process. So we have some XF. This is the spectrum, magnitude spectrum, and we do the up conversion to transmit it, and it goes through a channel. So this channel, you should note that it is going in terms of, and in this pass band, okay, at frequency FC. So after that we do the down conversion and it comes to this, then we decode this kind of signal. Okay. So here we are talking about the end-to-end channel for narrowband channel at frequency FT. So at frequency FT the channel is like this for a frequency flat channel. Okay. Now we talk about the direct channel. After the down conversion, it will have multiplication by this factor, e to the power minus j 2 pi fc into tau d. Tau d is what? Delay, direct delay between transmitter and receiver. Okay. Now similarly we can write the channel between nth element of the IRS and transmitter like this. Okay. Where this is the attenuation factor, this is the delay to reach from here to here, and this is the phase shift. Okay. Down conversion from frequency FC to baseband. Okay. And similarly we can write from for the IRS only, each IRS will have this kind of factor. Similarly we can write for the channel between receiver to nth element like this. So the effective signal will be like this, yk equals to h effective into xk plus wk. So this equation we obtained in the last slide here. So this h should be h effective when we are including IRS. So this is the direct path, okay, and this is what? This is the path via IRS. So we have n elements, so it will be coming, we will have this factor of n here, this summation n here, and we will have these three will be multiplied and they are in the exponential, so these will be added. Okay. So any question here in this slide? Okay. So let's only focus about the IRS signal here. So in IRS we have this the same thing here. Okay. The same thing I have written here like this. So using Cauchy-Schwarz inequality, everybody know about the Cauchy-Schwarz inequality, right? Okay. So if we write Cauchy-Schwarz inequality for this part and this part, so this is exponential, so its absolute value will be 1. So we can write like this. So what does it show? And this we can approximate like this. So what does it show? If we have n element, it is multiplied by a factor of n, and all the gains will be multiplied. So this is the gain, this is the channel gain from transmitter to IRS, and this is IRS attenuation, whatever it is, like 0.8 we see in the reflection coefficient, and this is the channel gain between receiver to IRS. Okay. So with these three will be multiplied, and we have this factor of n here. Okay. If we talk about in terms of SINR or power domain, so these will be squared here. So squared, and these gain will be multiplied here. Okay. So this equality will be achieved when these three are same. These three are integer multiple of 1 by FC. Okay. So these are some experimental result from this paper. Okay. So what they have done here, so they have the transmitter here, and they have the receiver here, and they have IRS here. Okay. So so this they have zoomed like this here. Okay. So this has the distance of 50 meter. So when IRS is not present, okay, so this is omnidirectional antenna. So the received signal is given by like this. So it is around minus 66 dBm. Okay. So we receive very little signal. Okay. And if we put the IRS here and configure it, it will reflect the signal to here, and we receive nice signal like this. So these have difference of like 25 dB or something. Okay. So and 25 dB is very large. Okay. 25 dB is very large to detect the signal. Okay. We can detect the signal very nicely here compared to here. So this this slide show the benefit when direct path is not available. Okay. So when we have one transmitter and one receiver and one IRS. Okay. So this path is minus 75 dB, this path is minus 75 dB, and we have two cases. First case is when direct path is not available, it means there is a blockage. So blockage will cause loss in dB more. So this path is minus 100 dB, and when there is a direct path available, it will be minus 75 dB. Okay. So these two cases, with and without IRS, we have seen here. So case one means when direct path is not available. So we see here with IRS we have this curve, without IRS we have this curve, case 1. So we see this much of difference we have when we increase the number of element. Okay. And when we have case 2, when this is 75 dB, we don't see much of difference here. Okay. So what does it show? That when direct path is not available, IRS is really helpful. IRS can be used to increase the spectral efficiency. Okay. And this factor n, so this increases like linearly with factor n. Okay. Any question here? Yes, n is the number of element. Yes. Gain is adding, that's what we have talked about here in this slide. So we have the sum here, so this is approximately equal to factor of n, and n will come here. Okay. So all gain, so between transmitter to IRS, this is IRS attenuation, okay, and this is receiver to IRS, all will be multiplied, and we will have a factor of n here according to this summation. Okay. So we can also compare with relay, how it compares with relay. So relay need a additional time slot. Okay. So if you know about the relay, so first we transmit some signal, relay amplifies this signal, do amplify and forward or decode and forward, okay. Then it forwards the signal. So it needs 2 time slot. So overall when we talk about the rate, the factor of half comes here. Okay. Half mean it takes 2 time slot. So overall rate is half, okay, for 1 time slot, okay, per time slot. So signal can be amplified at relay. This is one advantage of relay, okay. And in IRS, if we talk about it, we have all the 3 gains are multiplied, and we will have factor of n square here that we have seen here, right. Okay. So this will be n square when we go in the SINR domain, and we have relay. Relay gain is like this, factor of 1 by 2 is coming here, since it takes 2 time slots, 1 plus this beta SR and beta RD. So this is beta SR source to relay, and relay to destination, okay, minimum of it, okay. So here you see we are getting minimum of it, and here we are getting n square of factor of it. So this is better. So if we have value n is very large, then we can also beat relay, okay. So this figure show the required transmit power versus the distance to achieve this much. It's written here R bar equals to 6 bits per hertz. So this blue line is for DF relaying, decode and forward, and this is for CISO system. So when we have different values of n, so let's say for n equals to 150, last one. So we can see this is going after this, after a certain distance. So when we have low distance, this transmit power required is very less, okay. So when distance is going larger, transmit power required is more, okay. So here, how do we see this? So when we have increased number of antenna, it requires less transmit power, okay. Because we have IRS gain to cover for it. So when n will increase, it will require less transmit power to achieve the same rates, 6 bits per hertz, okay, 6 bps per hertz, okay. So this we have already talked about. IRS act like a convex lens rather than a mirror. So in this paper, this comparison is given. So mirror gain is like this. So this plot gives the total channel gain versus the number of element for mirror when we use IRS as a mirror, and when we use IRS as an optimal value of phase shift, okay. So this is like this, and after in the far field, so only point where an optimized IRS operates an anomalous mirror. So up to this point, mirror is better. So after this point, so when we have more number of element, we can go for the IRS optimization, okay. So when we have less number of IRS element, it is better to act as a mirror, okay. That's what it is saying. So we can just assign, so for example, this point comes at around 120 or something, okay. This is 100 or 200 or something, less than 200 it is coming. So it is saying, so around those points, if you have a number of points less than that, you can define your element so that it can reflect directly like a mirror, okay. So this is what we have discussed for conventional IRS, what IRS is made of, presented modeling of IRS, illustrated IRS experimentation, compared relay versus mirror. These are some future work. If you want to pursue further, you can use codebook based RIS coefficient, channel estimation. Can also use alongside relay also, relay plus IRS, what will be the performance. IRS is more useful when 100 gigahertz. So when we have a like millimeter wave, so in millimeter wave loss is very, very large, okay. So you can put IRS to cover for the losses, okay. So in above gigahertz is really helpful, okay. Huh? IRS? They have active IRS, but only passive IRS are only commercially available. Active IRS are not available. Active IRS, if you want to do, you have to implement yourself. Otherwise, it is not available. These results, they have used the active IRS. Okay. Should we go or it's okay? So, okay, so that's it for today. Okay. This is a very different stuff. Next slides. Okay, thank you everyone for listening. yes, it is also suitable for indoor, but it should be like a very large area. People are also working in the VLC also with mirrors and the IRS both also. So VLC is mostly for indoor. So people are working in that direction also. MATLAB code. So you can look for the ML Johnson website. They have MATLAB code also. Okay. Oh, no, I don't have it. They have it. They have it on the GitHub. You can go and they have it. I have seen that.
Where is it available, sir?
GitHub. GitHub.
Spell it out, sir.
GITHUB. Yeah, these are all Emil Johnson results. So they have the codes there. Eh? PPT? Okay, I'll forward.
You know, IRS, even though it's a lot of research going on, but you know, when we talk to Huawei big people, they say, you know, okay, IRS, you put IRS and reflect the signal to a particular user, but you may cause interference to other users. So that is always a problem as well. So I don't know how successful it's going to be in 6 users. So you put IRS to serve some users, but that IRS goes to other people.
Good afternoon, everyone. It's an honor and a privilege to stand before you today as we conclude this enlightening journey into the world of 5G and wireless communication technology. Today, as we bring this event to a close, we celebrate not just the end of gathering, but also the shared knowledge, collaboration, and inspiration that will undoubtedly propel us forward. As we have discussed during this event, 5G is more than just an incremental improvement. It's a paradigm shift. We learned wireless channel types, diversity techniques, multiple access interference management, increasing the capacity of the channels, capacity of MIMO, CMO, and massive MIMO, and simulations of all these topics. Let us carry forward the knowledge we have gained here and apply it to create solutions that benefit not just a privileged few, but society as a whole. I'd like to extend my heartfelt gratitude to the organizers, speakers, and participants who made this event a success. I'd like to thank all the participants for your patient listening and adjusting with the facilities here. Now it's time to invite our dignitaries onto the dais. I'd like to invite our beloved in-charge HOD, Professor L. Anjaneyulu sir, onto the dais. Welcome, sir. Now I invite Dean of IRAA, Professor S. Srinivasa Rao sir, to kindly grace the stage with your presence. I warmly welcome Professor Tam Ratnaraja sir to take the dais. I welcome our dear Dr. Kalpana Naidu ma'am onto the dais. I request our in-charge HOD, I request Dr. Navneet Garg sir to join us on stage. Now I request our in-charge HOD, Professor L. Anjaneyulu sir, to address the gathering.
Okay, yeah, I get, no, now I got it, how to make it on. Okay, good afternoon, all of you. Yeah, so the valedictory session, all the valedictory sections are supposed to be very brief sessions, okay, unlike inaugural sessions, because these are the sessions where people typically look forward for bye-bye, see you, take care, you know, so kind of things. And then people would always be in a hurry to leave after a huge sigh of relief, okay? But however, valedictory moments are the moments that are filled with gratitude and gladness for the kind of knowledge that you gained here from the experts. And also, it is the time, valedictory session is the time to acknowledge the commendable efforts put in by the organizers, the coordinator, Professor Kalpana ma'am, and the institute authorities who give permissions for conducting such courses. On top of all this, and the brain behind the program, Professor Ratan Raja sir, okay, stalwart in the field of 5G, and then you know, his efforts in sharing his knowledge to all of us is very much appreciated and commendable. They say knowledge is power, and then knowledge shared is power multiplied. Okay, in fact, we could witness that from the professor's talks. In fact, in the first day I attended, later on also I wanted to personally attend his talks, but somehow I could not make it due to the other official commitments. But however, I could follow him on YouTube channel on occasions. In fact, we are fortunate to have him over here for a week-long program, and then we really, you have really cherished his vast experience and the kind of knowledge that he shared with all of us. And then, because people like him, they enjoy by giving more than taking less. We should be more taker to give us than takers. That's truly evident from professors, a time that he spent over here. Okay, so that's one aspect. And in fact, in valedictory, we would like to hear more from you rather than we talk here. Whether we all could meet your expectations before you attended this course. With a lot of expectation that you have attended this course, that we would like to listen more from you. And then, since anyway the course is concluded now, and please share this knowledge with your students, and then share the knowledge with your colleagues, and then try to organize similar such programs at your institute. Please involve us, call us, and share your experiences with us, so that we'll be happy that this program, through this program, that we could help you in gaining knowledge in certain specific area. And I think that's all from my side. And let us be lifelong learners, curious forever, and and also try to improve ourselves as well as the world around us. Okay? So thank you so much, and then for being kind enough to attend this course. And then we need great minds and then kind hearts, be both of them. Thank you so much. Thank you.
Thank you, sir. Now I'd like to invite Dean of IRAA, Professor S. Srinivas Rao, sir, to deliver the speech.
Good afternoon to all. So, respected Professor Ratnaraj and Professor L. Anjaneyulu, head. I do, and the faculty, research scholars of Department of EC, and my dear participants who have shown interest to attend this 5-day GIAN course. So I hope all of you have listened lectures from Professor Ratnaraj, and you might have enriched a lot of information related to 5G and communication technologies. So your communication might have increased a lot by interaction with you, physical communication, as well as how effectively 5G communications can be used, and related to the software as well as hardware for communication structure. All those things you might have learned a lot for all these 5 days. Definitely there must be a lot of knowledge exchange might have happened for all these 5 days. So it should be utilized in a right direction for further generations of communication. Now 5G trend is getting slowly obsolete, and 6G, some people are doing research on 6G also. Like that, we don't know how many generations of this communication technology develops. Finally, it is making all of us comfortable. So whatever problems which are a theme of the topics identified for GIAN courses are not only related to the one state or one region or one country. They are global problems. As per the Government of India, the theme also should be useful for whole society as a whole throughout the world. So in that aspect, this program was planned, and because of the lot of cooperation and from this foreign professor might have materialized this program, and government, the panelists as well as reviewers have accepted this for conducting this 5-day program. And finally, we have to thank professor from Edinburgh coming all the way physically to engage the classes here and interacting with us. It is very good opportunity provided by Government of India. So all of you might have effectively utilized. So you cannot stop at this stage by listening only these 5 days. So you can interact with him for any other clarifications or research oriented problems or any further enhancement of your knowledge. Nowadays communication, you have already learned communication, so very quickly we can communicate within a minute. Once we press the submit button or send button, instantaneously messages are going throughout the world. So like simplify the communications. So all of you have to utilize whatever you have learned through this communication technology for further enhancing of your knowledge, so that the country has with this type of technologies. So once again, I thank the Professor Ratnaraj for coming all the way from University of Edinburgh to conduct these classes here for 5 days. And also I congratulate Dr. Kalpana Naidu for successfully conducting the 5-day program with the coordination and cooperation of all the faculty members and research scholars of Department of Electronics and Communication Engineering. Thank you one and all.
Thank you, sir, for your valuable words. Now, I have the privilege of inviting our distinguished resource person, Professor Tham Ratnaraja, sir, to share the valuable insights with us.
Hello, good afternoon, everyone. Thank you, Dean Srinivas Rao and HOD for hosting this event, and also thank you to Kalpana Madam for organizing this event. And thank you all for listening for last 5 days to my talk. I think I have talked enough already for last 5 days, and also I like to thank Professor for taking me to the to show around Warangal area as well. I think I enjoyed last 5 days teaching you guys, and look forward to do some more collaboration and publication in the future if you are interested. Okay, thank you all for being with me for last 5 days.
Thank you, sir. Now I'd like to invite Dr. Navneet Garg, sir, to deliver his speech.
I want to thank you, Professor Ratnaya, for inviting me. Also Kalpana ma'am for organizing such a nice event in a nice and wonderful way. And I also want to thank the participant who have listened me very well, patiently. And Professor Sai Prakash Garu, he has taken us to the city, and everything was very good, and I really enjoyed it. Thank you very much.
Thank you, sir. Now I request the participants to share the valuable feedback on the event.
Yeah, this is oral feedback.
Hello.
Yeah, please come on.
Yeah, please don't worry. Even if it is negative feedback also, you are welcome.
Good afternoon, dignitaries on the dais and off the dais. From this course, we have learned.
Mic is not switched on.
We have learned so many concepts, things which we were about to learn for our research. Actually, what we were in a research field, we are the new to this research field, wireless communication. So basic concept of what to learn, how to go progress in our research, that we got. And here everyone is have abundant knowledge. Our resource person has so much of abundant knowledge. We hope we'll get the same kind of what you can support in our future too. I expect that kind of a support from all the resource person, and everyone is here have the abundant knowledge what we felt. So it's a great opportunity, and it's a very this hall is full of knowledge. I can say learning, and throughout the lifelong it is a learning journey. So we learned so much from this NIT Warangal. Thank you so much for organizing such kind of courses. Thank you, ma'am, for all this kind of support. Thank you, ma'am.
Thank you.
Maybe from him. He's also one of the
Very good afternoon to all the dignitaries on the dais and off the dais, my colleague who are participants for this workshop. It gives me immense pleasure for attending this program. Many of our faculty are not able to attend IIT professors' lectures or even foreign professor lectures. So this provided an opportunity to attend to the professor who is eminent in this communications and signal processing from Edinburgh. Thanks for the administration, NIT Warangal and coordinator Kalpana Madam providing this good opportunity. After listening to attending to this workshop, as a faculty I have a little bit of knowledge, and now I will take forward and I will accelerate my research, and even I will guide my students in this direction. It is a great learning, sir, and you have given a very good mathematical analysis. As a signal processing professor, you have given some of the things we got very good. And also your student and young researcher, he has given a good simulation results, and he has shown all the things. It is a great learning for all of us. Thanks for the for you to come to this NIT Warangal, and also I would like to thank HOD of NIT Warangal and all the admin for providing this opportunity for all our faculties. Thanks a lot. And as madam asked, negative feedback is also okay, but as we came from long distances, accommodation bit inconvenient we felt. So in the next upcoming conferences, because we are also faculty age-wise also bit elders, so a little bit inconvenient we felt in the accommodation. Course-wise it is extraordinary, but a little bit inconvenient in the accommodation. Small things, okay, then it will become good. And also I would like to thanks all the professors of Department of ECE. I'm basically from Vignans University, sir, located in Guntur, and all the many professors are supporting for our university in the form of BOS, DRC members, and so many activities. Thanks for the NIT Warangal. Thank you so much.
Others, please give feedback.
Good afternoon, one and all on present over here. I am coming from myself Hemlata M. Me and Kalpana ma'am, our colleague coming from Kongu Engineering College, Tamil Nadu. We are traveling around 1,000 kilometers nearby to participate in this program. So we are very, very happy to deliver that. We enjoyed thoroughly and also got more benefits from this program. We are from computer science engineering field, but the topic just admiring us to participate here. And Kalpana Naidu ma'am, a one-man women army who conduct this event very in efficient way. So part of the negativity, but you're very awesome to conduct this kind of program to us, and multilingual communications were there. So we are thoroughly enjoyed. 5 days gone like a 5 minutes to us. Fruitful memories are there. That word tea getting cold. This word can't forget by us. We thoroughly enjoyed it. Thank you so much for one and all present here. Thank you.
Thank you, madam.
Anyone?
Sir. Yeah, anything, sir. Yeah, if you want to come, please.
Honorable dignitaries, honored as respected resource person Tharam Ratanaja sir, respected in charge HOD Professor Ella Anjaneyal sir, respected Dean International Affairs, International and International Relations Alumni Affairs Srinivas Rao sir, and respected co-speaker Dr. Navneet Garg sir, and respected Professor Sai Prakash sir, and all my fellow participants, good afternoon one and all. I'm sorry, respected coordinator Dr. Kalpana ma'am. First of all, I would like to thank Dr. Kalpana ma'am for conducting this workshop, and I also thank Professor S. Srinivas Rao sir for giving consent to conduct this workshop. So actually, as a part of this program, I am currently pursuing my research in 5G communication. I am much more interested and I request Kalpana ma'am to conduct much more FDPs in near future also. And one point I would like to share with you all, like we want more research oriented topics or any program simulations or how to write research papers, and that we are expecting ma'am. So in near future, like if you can conduct many more such FDPs, we'll be really thankful to you, ma'am. And a special thanks to Ratnaraja sir. It's not that easy to travel all the way from London to Warangal and spend 5 days, because sir's time is really very valuable. So spending his time for 5 complete days, and along with him Dr. Navneet Garg sir, both of them spending such a huge amount of time with us is not that easy. Thank you so much sir from my side, and also on behalf of all the participants. And starting from the day one, the first lecture, the overview lecture given by Professor L. Anjaneyar sir, it was really very good. We have noted many points during the overview lecture itself. Thank you, Anjaneyar sir. And even the Professor S. Srinivas Rao sir, our Dean International Alumni Affairs, sir also has given the overview. We request the Dean and the in-charge HOD and all the EC department fraternity to conduct many more such workshops and FDPs in wireless communication domain in future also. Thank you for giving me this opportunity.
Thank you all for giving your valuable feedback. Now it's time to invite Dr. Kalpana Naidu ma'am for vote of thanks.
Other feedback? Yeah, no one wants to give feedback, huh? Yeah, even if it is negative feedback also, you are most welcome. Yeah, namaste to all of you. Yes, namaste sir, Dharmratna Raja garu. Namaste Anjaneyar garu, namaste Srinivas Rao garu, and namaste Navani sir. And namaste to you. So what to say, I will speak informally. Yeah, first of all, I have to thank GIAN course coordinators, national coordinators, that means IIT Hyderabad, for sanctioning me this project. Because without them sanctioning this project, yeah, I won't be able to conduct this GIAN course. So I have to thank first of all IIT Hyderabad, Anil Kumar garu. I don't know, he must be professor there. So Professor Anil Kumar garu for sanctioning me this project, and also, yeah, Professor Srinivas Rao garu for cooperating with me entirely during these 6 months. Once the project is sanctioned, yeah, he has conducted so many meetings with all of our professors who were sanctioned with the GIAN projects, and he has conducted meetings, and he tried to reduce the overhead charges also from the institute, and he tried to help us like anything. Yeah, and yesterday also, sorry sir, I have to tell sorry to him, because now what happened means, whatever you have given, whatever you have filled as your names in the Google form, same thing I have sent it to the printing of your participation certificate. Yeah, in that, yeah, someone has filled it as NITW, some other participant have filled it as NIT Warangal, some other participant have filled it as, yeah, so many, same institute name, but differently. Yeah, that's what he has pointed out. Of course, I did not check thoroughly. Yeah, but anyway, for that I have to tell sorry to Srinivas Rao garu and other things. Yeah, Anjaneyar garu. And Navani sir. Yeah, thank you, sir. Anjaneyar garu and other department faculty colleagues, yeah, they have helped me like anything. In these 5 days now, even though grades meeting was there, I did not attend even for single minute also. 1 minute only I went to the grades meeting and I came back immediately. Yeah, for that I have to thank all the department colleagues. And another thing that is most helpful to me is some of the faculty members directly asked me if I can utilize their research fellows, because I don't have currently, a single research scholar also, because whoever research scholars I had, yeah, they went out after submitting their thesis, so I had no one to help me. So many other faculty members have asked me directly if I can utilize their research scholars. Yeah, that's why I want to thank all the faculty members who tried to help me during these 5 days, and other Anjaneyar garu. Thanks, sir. Yeah, actually what happened was, yesterday I went and requested him, even though he was there in the grade meeting, yeah, asking him to come to the valedictory function. What he told is, yeah, I was busy, I'm busy a little bit. Yeah, he has an online meeting today also. Yeah, but he told immediately that, yeah, he requested, he said that he doesn't want to come because he had online meeting. But again, I requested for the second time. Yeah, then as soon as I requested him for the second time, he accepted immediately. That's why I want to thank Anjali Garu for coming here. And others, yeah, I forgot you. Yeah, thank you. I mean, even though I have put in so much effort, I have mailed so many persons. Yeah, but for those mails, you have responded. You have responded. For your response, I have to appreciate you and I have to thank you. I have to thank you because without you participating in this course, there won't be any use, even if it is sanctioned also. Yeah, thank you for coming all the way. Yeah, as that madam said, she has come, I mean, all of you have come from Erode to Warangal, right? Yeah, thank you, madam, thank you. Thank you so much. I mean, I'm not doing this, I'm praising you. What and all other things I have? Yeah, about negative feedback. So, I mean, please, yeah, yes, some of you have faced problems in the accommodation. That I have to agree, but why you must have faced the problems means, I told you already in the inauguration function itself, yeah, there were so many alumni meetings were going on. I mean, 1 or 2 conferences are going on, 3 GIAN courses are going on at the same time in different departments. So all those course faculty members have booked the guest house with no facilities to be provided for you. I have requested the guest house people like anything to provide accommodation for all of you in the guest house. Yeah, but they told that already everything is reserved, every room is reserved in the guest house. So I could not find any proper accommodation for you. I'm really sorry, Really, I feel sorry for you. Of course, as you are our guests, we have to provide something to you, something nice. Yeah, even though it is not best, yeah, at least little bit better we have to provide, na? Yeah, some of you I know, especially ladies. Yeah, you have faced many problems, I know for the accommodation. I'm very sorry for that, but I hope you are okay now, because you are leaving. Yeah, I'm very sorry if you have faced any discomfort. And other things. Did I forget anything? Yeah, another negative feedback. Another negative feedback is conducting the lab sessions. Yes, I have read the written feedback also. Yeah, some people have asked, some people have given the feedback saying that we did not have the lab sessions. Yeah, we had lab sessions. If we have practice sessions, what happens? You will be able to practice one or two programs. But what we had here, simply, I mean, they have delivered what and all, Professor, I mean, Navneet Garu have delivered whatever he is doing as a current research. All those programs he tried to give. And I have given 1 or 2 programs only, I think. I mean, because all those programs, even by changing little bit also, you'll be able to submit 1 research paper. So when compared to the conducting lab sessions, it is always better, because you will be able to further your research there by taking the suggested programs, suggested MATLAB programmings and all. And other feedback regarding 5G, any other feedback you have given? I did not read all the things, but anyway, if there are any shortcomings, yeah, I'm sorry, extremely sorry for that. Yeah, but at the same time, I tried to comfort you, I tried to give accommodation to you, I tried to do everything possible to the best of my thing, to the best of my ability. That much I can assure you. And other things, I have to praise Professor Dharmaratna sir, because what we have planned initially, we have planned for theory courses only, I mean theoretical part. Yeah, but after coming here on the 2nd day or 3rd day, some of you have suggested that it is going in the theoretical way, in the lectures way. So please convert it into research, we want research. Yeah, as soon as you have told me, I asked him to go in the research way, not in the teaching way. So as soon as I informed him, yeah, he had changed his mode entirely. He must have prepared so many PPTs before coming here. Yeah, as soon as I told him they had to do night out. I can understand they had to do night out and they had to change their course. They had to prepare PPTs and they had to practice MATLAB programming. All those things they have done. I mean, with one word from me. So they try to accommodate you like anything to provide the research research abilities to the participants. So thanks, sir. Ratnaraja garu. Thanks Andy for that. Thank you, Navani sir. I don't know if I forgot. Yeah, I have to tell thanks to all these guys. Yeah, my JRF, Mubina, I mean, she listens to me like anything. Even though she has work, she tried to comfort me and she tried to do all the things for me because I don't have any PhD scholars now. And the other one, Vijay, M.Tech student, yeah, he also tried to do one or the other things, even though I did not tell them to do even a single thing also. And others, yeah, Sridevi, yeah, she is a PhD scholar from other professor. Yeah, she tried to help me. She does anchoring, she did anchoring, and she tried to give you so many things, and she tried to accommodate my requests also. Yeah, thanks, Sridevi. And Srivenila. Srivenila also is a PhD scholar of other professor. Yeah, thank you, Srivenila. And others. Yeah, thank you, Sai Prakash Garu. Yeah, thank you, Sai Prakash Garu. Huh? Venkat, who is that? Yeah, okay, obviously, because he is my husband, he has to do the things for me, na? And who else I forgot? Yeah, non-technical staff. Even non-technical staff also, they try to accommodate me like anything. Yeah, thanks Reddy Garu and వేరే వాళ్ళ పేర్లు నాకు గుర్తులేదండి. Kumar Garu, Venkat Garu and others, sir. Rupa Garu. All the non-teaching staff, thanks, sir. Yeah, did I forget anyone? Recording persons. Yeah, even though there is no wrong. I mean, if I forgot anyone, sorry for them. But all the guys and girls who have helped me during these 5 days and before these 5 days also, I have to tell thanks to them. Thank you. And thank you to all of you. Yeah, that's all. Thank you.
Thank you very much, ma'am. Now it's the time of distributing the certificates. I request Professor Srinivas Rao sir for distributing certificates to the participants. Jahnavi, Katragadda Jahnavi, ma'am. Please join Dharm Ratnaraja sir and also Navneet Ghat sir and Anjanelu sir also for distributing the certificates to the participants. Michael Suganakumar, Sai Kirtana, Ready sir, certificates తీసుకోండి అటు ఇవ్వండి ఇటు నుంచి సాయి కీర్తన రమ్యశ్రీ జి రమ్యశ్రీ డాక్టర్ పి సుధా శ్రీ సుధా రమాదేవి ఎం Dr. KLV Sai Prakash Sakuru. T. Sridevi. Vijay Shanti Narni. Dr. S. Mohandas. Dr. Pichaya. Rekha Saboji. Dr. M. Prem Kumar.
We'll check you up if your names are there or not. I mean, they are giving other participant certificates to you.
G. Ramya. Hemalata M. Satish Kanapala. Dr. Ravi Kumar. Purnima Patil. Pallavi S. Hiremat. Dr. Satyanarayana Murthy Nimmagadda. Ramadevi M. Naga Srinivasrao Chilamkurti. Naga Srinivasrao. SVMG Fanikumar. Swati Govindu. Vijay Shanti Maddineni. Dr. Kalaivani R. Mekala C. Afzal Ahmad. Kalpana R. Chakradhar Pasupaleti. Sirivanilla, myself. Thank you, sir. Please. We'll close the event with national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा शुभ नामे जागे, तब शुभ आशीष मांगे, गाहे तब जय गाथा, जन गण मंगलदायक जय हे भारत भाग्य विधाता, जय हे जय हे जय हे जय 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 हे।
GIAN stack sir outside, please speak.
Yeah, participants, please check if your names are there on your certificates. If your name is not there, please, please communicate with the respective person and get back your certificate.
Choostam sir, choostam. Thank you sir.